Now that we have seen not only the Jacobian matrix, but also the Hessian matrix for functions which are differentiable functions of n variables and which are scalar valued, we are ready to look at the Taylor series approximation for such functions. I would like to do this by first revisiting very quickly the idea of a Taylor series for a function of one variable. I expect you've seen this before. If you have never seen Taylor series, I have several videos about Taylor series. I think you should work through them first. So let me quickly put up here as a reminder what the Taylor series for e to the x centered at 0 looks like. So we say that e to the x equals a 0th order term, that's 1 here, plus a first order term, then a second order term, third order term, etc. Each piece in a Taylor series looks like a polynomial, but this is not a polynomial as long as we have infinitely many non-zero terms because it goes on forever. But the idea is that this presentation where, truncating it and looking at maybe just a few terms looks like a polynomial may give us techniques and ways to approximate that we don't have when we start with the, say, nonlinear function. Okay, so that was a quick review of Taylor series. I want to make a notational comment here. We can take a Taylor series and truncate it, as I said. So here I have still the the 0th order term, the first order term, the second order term, and then I want to roll everything else and collect it all into a notation that means, and it keeps going, but in a way which we can describe as being dominated by one particular component. So for a truncated Taylor series, we often write something like big O notation, big O of x cubed as x approaches 0, to mean that as x approaches 0, so imagine x to be very, very small in size, the rest of the series, what we cut out when we stopped writing after the quadratic order term, is dominated by what's inside this big O argument. So big O x cubed, I would think of it here in this context as x cubed factors out of the rest of the Taylor series expansion for e to the x, leaving us with 1 over 3 factorial, so that's a constant, plus, if I factor x cubed out, x over 4 factorial, etc. And as x goes to 0, these terms, which all contain an x, they vanish. So you think of this leading 1 over 3 factorial as like the most important governing piece of this expression. So in this context with truncated Taylor series, it's like this big O notation means that the rest of the series is really dominated by this x cubed expression. Okay, with this, I'm going to keep talking about notation for functions one variable for just one more slide, and then I will write down how we will describe the Taylor series for a scalar value function of multiple variables. A moment ago, I showed you the Taylor series for the exponential function centered at x equals 0. I hoped that that would remind you of what they look like because that's one of the most famous Taylor series of all. In general, how we compute a Taylor series for a function which is infinitely differentiable is we compute what are called the Taylor coefficients. So the degree n component of that infinite polynomial-looking expression is computed by taking the nth derivative of the function evaluated at the center point. So here I'm going to move away from 0 and just imagine that we're centering our computation at p. So compute the nth derivative of f at p, divide that by n factorial. That's something I often forget, so I assume other people do as well. But you got to divide by that n factorial and then multiply it by x minus p raised to the n. So here we have a number. So after you compute the derivative, you plug in p. So this is a number that's called a coefficient. And then here we have this polynomial component, x minus p raised to the nth power. In order to have a Taylor series expansion, your function must be infinitely differentiable because you have to keep differentiating it to get these kinds of coefficients there. I don't want to go too much into when is a function equal to its Taylor series expression here. We do have that for the exponential function, so I wrote that as equality. I said e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, et cetera, et cetera. In general, that might not necessarily be the case, even if your function is infinitely differentiable. In order for a function to be equal to its Taylor series representation, we would need the function to be real analytic, and that's as much as I want to say in this particular video. Moving along to the idea of, say, a Taylor series approximation, I like to denote with subscripts And for me, the only ones I ever really use are T sub 1 and T sub 2 because I'm usually most interested in first order and second order approximations. So I denote with T sub 2, for example, the Taylor series approximation, the Taylor polynomial you get if you only go out to the quadratic order term. So here, I'm not letting this go on forever. I'm cutting it off after the quadratic order term so that we have 0, first, and second order terms. That's a real polynomial. So this is a quadratic polynomial, and that could be used to approximate your function near p. T sub 1, if you write down the equation for T sub 1 for a function of one variable, should look familiar. It's actually the tangent line, and that's something that we work with all the time. So T sub 1 centered at p is your tangent line to your function at p. This you could think of as your tangent parabola for a function of one variable. Okay, let me pause here for a moment if you're writing this down, and then I want to come back and take the second order piece, and I just want to rewrite it in a way which seems really silly at first, but it will lead into how we will write down the second order component when we come up with the second order Taylor polynomial for functions of multiple variables. Okay, before we look at functions of multiple variables, let me take this piece and write something which is equivalent to it. I just want to rearrange these terms. If you have never seen the Taylor series for a function of multiple variables, you might think that I'm doing something incredibly silly, but I think it helps you extend this well-known concept from calculus into the multivariable setting. So let's take this piece here. And what I would like to do is recognize that this is a product of scalar terms. So it's written here in the most natural way possible, leading scalar coefficient times x minus p squared. I'm going to rethink of this as a triple product. I'll stick with this color, where let me just leave the 1 over 2 factorial out front. And then instead of a number times this polynomial piece, I'm going to write it as a product of three things. The first is x minus p. The second is the second derivative of f evaluated at p. And then the third is x minus p again. It's the same piece. I've just reordered the terms. And then if you want to be really strange, what you could do is say, let me take this x minus p piece here, which is a number, and transpose it, because any number is equal to its own transpose. It's just a little 1-by-1 matrix. Okay, so this seems very strange, but now if you're watching this after watching the video about the Hessian, which we know is a bilinear form acting on pairs of vectors, and we talked about what that action looks like, you may recognize this as similar to the matrix triple product that we explored with the Hessian matrix. And that's exactly what we're going to do now, is take this second order expression and write it for a scalar value function of multiple variables, where each piece is going to translate very naturally to, the 0th order term. The first order term is going to lead to the Jacobian or the gradient if you have a preference there. And then the second order piece will look like that action of the Hessian matrix on pairs of vectors. And now we can say it looks exactly like it does when we have single variable functions, as long as we think of it this way. Now that we have quickly reviewed Taylor polynomials for scalar valued functions of one variable, let's look at their analogs for scalar valued functions of multiple variables. So imagine that we have some function f, which is a scalar valued function on some open domain A, which is, say, a subset of Rn in dimensional Euclidean space. And we would like to write down Taylor polynomials centered at some point P. We imagine that f is nice enough that we can take some derivatives. So, for the T1, you would want it to be at least differentiable, continuously differentiable. For T2, we'd like for it to be class C2, etc. In a moment, I'm going to write down the general Taylor's theorem, and in that you will see the form of the degree k Taylor polynomial. I don't think it will surprise you, but before we do that, let's just highlight these two specific cases because they're kind of the ones we see the most. So we've got the first order approximation T1, and then T2, which is like your quadratic approximation. So for T1, centered at P, we want to say that this degree 1 approximation, which is giving us an idea of how f behaves near P, looks like f of P plus, let me start by writing the Jacobian rather than the gradient. So df at P times the vector x minus P. Okay, couple remarks here. Maybe the first remark is that this is just fine as it is. You're ready to use this right away for a vector value function. So here, I'll say vector value is exactly the same And let me explain why I'm kind of separating this case out separately when we talk about T2 in just a moment. If it is scalar valued, then you don't need to use this general Jacobian language here. You could say that that is actually the gradient of f at p, and this matrix product, if you switch df to the gradient of f, turns into a dot product. Yeah, let me write that too. So this is equal to f at p plus the gradient of f at p. That's something that you only talk about for scalar valued functions, dot, so traditional dot product, x minus p. And this is only for scalar valued functions. Okay. Basically, this first order tangent, this first order Taylor polynomial is like your tangent line. It's like your tangent plane. In fact, it's what we've been calling the first order approximation as we've been assessing differentiability of functions. So let me write it over here. We've been characterizing differentiability for functions as saying that the difference between f of x and this expression, its first order approximation, which we can now characterize as just t sub 1, this distance must shrink to 0 and shrink to 0 so fast that when I divide it by the vector norm of x minus p, the center p, this ratio goes to 0 as x goes to p. So if the limit of this quotient is not 0 as x goes to p, f is not differentiable at p. One way you can characterize the behavior of this limit to say this ratio goes to 0 as x goes to p is to say that this expression, so like the error between f and its first order approximation, this expression is little o of the distance from x to p. So this sentence here translates into this limit. Okay, this should all be fairly familiar because we've been looking at differentiability for a while. So we've been computing these kinds of limits. We've worked with this first order approximation already. For our second order approximation, this is kind of new, but it also is something I think that you're anticipating based on our discussion of the Hessian and what we just looked at with degree 2 Taylor polynomials for functions of one variable. So we're going to take this and just add onto it a quadratic term. In fact, let me write T1 of x, meaning all of this, plus a second order term. So that's 1 over 2 factorial times x minus p, this vector transposed, times the Hessian at p, times x minus p. This second order approximation exists for vector value functions as well, but as I mentioned when we introduced the Hessian, if you have a scalar valued function, your Hessian is a matrix. If your function is vector valued, it still exists, but it's something you can think of as like a tensor, and that's not a dimensional object that we're going to work with in this particular curriculum. So here I'm really assuming that I'm working with a scalar valued function. Okay, so this was one way. I'm going to rewrite this T2 if you don't like this in just a second. But basically, you take these two terms that we already have. So this is T1, and then add to it this degree 2 term. Just to rewrite this, this is f of p plus the gradient of f at p dot, dot x minus p, so that's vector dot product, plus 1 over 2 factorial times the Hessian acting on the pair of vectors x minus p, x minus p. And that is the form that we will put it in just a moment. So this is a bilinear form, and it acts on x minus p paired with itself, where that action is this matrix triple product. Okay, so we have our first and second degree Taylor polynomials. Again, I think that this is probably what you expected based on the discussion that we had with scalar value functions of one variable. I have examples after this video of computing this for explicit functions. So I think I have a couple of them, and we'll have just a function f, and we'll compute T2. And also, we want to check that the remainder, so the error between f and its second degree Taylor polynomial is little o of the distance of x minus the distance from x to p squared. So let me see if I can write that here. I'm just worried about putting things next to each other, which are not actually adjacent. And here, we want this error, the error between our function and our t2, to satisfy that the size of this error. You can omit these absolute values, by the way, because this numerator is just a scalar. But this divided by the distance from x to p squared goes to 0 as x goes to p. I hope you can read that. X minus p is going to 0. So if we square something going to 0, it's going to 0 faster. So notice this denominator is vanishing faster at like a higher level than this one. So this numerator needs to be shrinking even more than this one. It's like your tangent quadratic approximation. It's got almost like a higher level of tangency than the first order approximation because it's harder to satisfy this than this. And again, this notation means that this term, the numerator here is little o of this quantity in the denominator. Sorry, I'm trying to write down there in the bottom right corner. And I am apologizing. I think that's gone off the screen. But we will now state Taylor's theorem, and we will do a quick proof of it. And here is Taylor's theorem for a scalar valued function of multiple variables. There's a lot going on here, so this is just one big theorem that I've written out. So take a moment to pause and just read through it. Think about what the difference is between these two lines. So I broke this up into two lines on purpose. See if you can determine why I did that. And also just ask yourself, like, what is this theorem saying? And then I will come back and talk you through it. The context is a function which is nicely differentiable. In fact, we're going to assume it's Cn. So n times differentiable with nice continuous derivatives on some open domain A in Rn. So I'm overusing the letter n here. So we have R little n is the dimension of the space. I'm not going to really mention that again. And then C capital N is the class of this function. We have chosen some point P in the domain where we are centering this part of the computation. So what we are building up on the first line here is the degree capital N minus 1 Taylor polynomial for this function centered at P. I have kind of separated off the 0th order term. So we have just f of p, that's our 0th order term in our Taylor polynomial. And then if you started to expand this sum, the first one would be 1 over 1 factorial times d1f, so that's the Jacobian. So just df at p times x minus p. So that is your first order piece. The next piece would be 1 over 2 factorial times d2, that's our Hessian. So the Hessian of f at p acting on the pair of vectors x minus p, x minus p. So we'd have that bilinear form acting on a pair of vectors. If we kept going with this, our next piece would be 1 over 3 factorial times d3 of f at p acting on a triple of vectors. So that's a trilinear form acting on x minus p paired with x minus p and x minus p. And you could keep going up to, say, capital N minus 1. You're not required to go that far. So maybe your function is smooth, but you only want to write down a few terms here, and that's fine. So I'm not saying that you have to include all of these terms in your expansion. But what you formed is some Taylor polynomial up to degree n minus 1. And then down here, we have the error. So this piece down here is like the gap between the true value of our function at x and this degree capital N minus 1 Taylor polynomial, or whatever degree you've picked. Whatever degree you've picked, the derivative expression down here is just one higher. So while I've written capital N minus 1 and capital N, I hope it's clear that you could be doing like through the third degree, and then this would be d4. I forgot to say the most important thing, which is that the x where we are evaluating this. So, we've we have our Taylor polynomial centered at P, and then we're trying to use that to estimate the value of our function at X, what we want to do is pick X so that it can be connected to P in the domain with a straight line that stays in the domain. Okay, so we have the center of our Taylor polynomial, then we're saying, okay, let's use that to approximate F here. Perhaps I know a lot about F here, but I don't know a lot about F here. So we're going to use this Taylor polynomial to approximate F of X. This is some kind of error between our approximation and the true value of the function at X. Again, let me pause for just a moment. And if you're with me and you thought about everything, great. Otherwise, you can kind of digest what I was just saying. But in addition, think about this C, visualize it, and see if it reminds you of anything. All right, so we are trying to estimate f of x with this expression. And this is what you think of as like the error or the remainder. I have a video where I talk through Taylor's theorem for functions of one variable, and I give you 4 different versions of the error, and I do a proof for each one. So it's a pretty proof-heavy, rigorous video, but I look at Peano's form, the integral form, Cauchy's form, and Lagrange's form for functions of one variable. This is Lagrange's form of the remainder for functions of multiple variables. And the reason why is because it's my favorite. And the reason it's my favorite, the main reason, is that it looks the most like the rest of the terms in the Taylor polynomial, almost confusingly so. So if you read it too quickly, you might think that this is the degree in part of the Taylor polynomial, but it's not, because df is not being evaluated, dn, the nth level differentiation operator, is not being evaluated at p, but rather at some c, which sits on this line segment between P and X. So let me put C. My uncertainty there was because it doesn't tell you where precisely on this line segment it lives. So, it could be here, it could be here. It doesn't tell you like how to compute that, nor does it tell you that this point is unique. So maybe there were multiple points that could be used in this expression in order to make this equality true. That should remind you a lot of the mean value theorem for regular functions of one variable. I actually have a video where I do the mean value theorem for functions of multiple variables as well, which are scalar valued. So if you wanted to, you can get the mean value theorem out of this. Taylor's theorem is really like a generalization of the mean value theorem. And how you would get the mean value theorem, let me just write the version that is for functions of multiple variables, of which the scalar valued version is just a special case, is you would have the 0th order term and this. So you would say, okay, degree 0, and then I wrote this as if you have to have a degree 1 term, but you don't. So you could go from this to this. You could have 0 first order and then a second order, 0 first, second, and then a third order. You can pick how many of these terms you keep until you truncate your Taylor series expansion. Okay, probably saying a little too much. Let me just write down the MVT. So this is like saying f of x is f of p. And then if I stop my sum at 0, my next term would be 1 over 1 factorial. I'm not going to write that. d1, so df at c x minus p. And that is exactly the regular mean value theorem. So it's just one special case of Taylor's theorem. Taylor's theorem is a way to generalize this mean value theorem idea to having more terms here in your Taylor series expansion. So this is like the 0th order plus a first order remainder, but you can do more than that. In just a moment, I'm going to wrap up this video with a proof of this statement. It's going to rely on the proof that I did in the video for functions of one variable. So I will assume that we already know Taylor's theorem with Lagrange remainder is true for functions of one variable, because we will actually reduce the problem to a function of one variable. And also, I'm going to work through the first level differentiation, the second level derivative, and then I'm just going to make kind of a claim. So it's not going to be a fully done proof, but I'll give you a sketch of the argument. We are looking for a behavior that will exist on this line segment. So the first thing we need to do is describe that line segment. There's a very standard way to parameterize a straight line. And that is to let r of t be 1 minus the parameter t times where you start, plus the parameter t times where you finish. You can check that r of 0 is p and r of 1 is x. Moreover, let me just write it here. R prime of t is the constant vector x minus p. And since that vector is constant, all other derivatives like the acceleration and beyond will be 0. Okay. That is a parameterized path now in the domain of our function f. So since it lives in the domain, let's plug it into f. So we will do the composition f of r of t, and that's actually going to be a scalar valued function of one variable. So let me name it h of t. So from t values going from 0 to 1, r of t puts us here, and then we plug that into f, right? So f is scalar valued. Ultimately, this is scalar valued, but it's also a scalar valued function of just one variable, which is why I'm going to cite the Taylor's theorem proof that I did in a separate video for functions of one variable. Okay, with this composition, we're going to need to take any kind of derivative of it, basically, but I'm only going to explicitly work out the first two, and then I'm going to make a claim. So the proof is a little bit incomplete, but I'll leave it to you to fill in the details for higher level orders of differentiation. So let's work out h prime and h prime prime at 0. Let me call it h prime at t first, and then we'll plug in 0. By the chain rule, it's derivative of the outside evaluated on the inside times the derivative of the inside. Since f is a scalar valued function, let me go ahead and put this in gradient form, like that. So it's the gradient of f evaluated along r of t dot the velocity vector. Let me skip down here to put the second derivative. I need to differentiate this. So here we'll have a product rule, but that's good because r double prime is 0, so one of the terms will vanish right away. And then to differentiate this is actually going to give us back our Hessian, but let me do that. So d of the gradient of f at r of t dot r prime of t plus the gradient of f along r of t dot the 0 acceleration vector, so we don't have to stick with this. Okay, now this is exactly the form that we use to derive the Hessian matrix. So we said that if you differentiate a gradient, you get the transpose of the Hessian. So that's going to be the Hessian of f evaluated along r of t transpose times the velocity vector r prime. So that is the chain rule applied to this composition in here, dot the velocity vector. Okay. Let me now plug in t equals 0. When t equals 0, h prime of 0 will be the gradient of f at r of 0, which is p. And whether we plug in t equals 0 or anything else, the velocity vector is the constant x minus p. You might recognize this expression I'm writing down, and you will really recognize it for the second one. So if I now evaluate the second derivative of h when t equals 0, we get, let me not do too much in one go. Let's just go ahead and plug it into this. The Hessian of f at r of 0, which is p, we are going to transpose that and matrix multiply that with the vector x minus p, and then dot that with the vector x minus p. Okay. That is the action of the Hessian on a pair of vectors, but to really see it, what you can do is take this matrix product and transpose it. So when you do, each of the terms will get transposed and you flip the order, which means, and then what was a dot product here will become matrix multiplication. So I'm going to take this vector dot product, transpose the first one so that we get a matrix triple product. And it looks like x minus p transpose, the transpose of the Hessian, so that's just the regular Hessian, times x minus p, and that is the action of the Hessian on the pair of vectors x minus p, x minus p. And then it's like, well, what would happen if I did h triple prime? Here we have it's like you could write this as the Jacobian acting on x minus p. Here it's the Hessian acting on the pair x minus p, x minus p. So it's my claim over here will be that the kth derivative of h at 0 is the kth differential operator at p acting on x minus p with itself k times. Like that. Okay. But I'm not going to go into that because we haven't talked about any of these operators higher than the Hessian. So I will leave it here and kind of step away from this. Let me pause because I need to erase this. And then what we are going to do when I come back is write out Taylor's theorem for H. So don't want to put in P and X to H because H's domain is this parameter space. So what we're going to do is center the Taylor expansion for H at 0. So analogously, like P will get mapped to 0. And then what I think of as stepping away from that will be 1. So it's like we'll have H of 1 equals H of 0 plus H prime at 0, 1 minus 0, et cetera, et cetera. So that's how we're going to proceed, is write out a Taylor expansion for H centered at 0. Let's now apply the one-dimensional Taylor's theorem with Lagrange remainder to H. First, let me point out that since f is a class C capital N function and that parameterized line R was smooth, H is also Cn. So f is Cn on the domain A, and R is smooth. H is class Cn. Okay. Now we are going to write down that Taylor expansion centered at 0 for H, and I'm going to use it to approximate H at 1 with a remainder, which will be Lagrange's form of the remainder. Maybe it's helpful if I just go ahead and write it down. Then, by prior result, our discussion about Taylor's theorem for functions of one variable, we can say that there exists some parameter value. Let me call it tau, like I did in the mean value theorem proof. Tau between 0 and 1, so that h of 1 is h at 0 plus h prime at 0, and then look what happens here, it's 1 minus 0, plus 1 over 2 factorial h double prime at 0 times 1 minus 0 squared plus dot 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 plus, and then let me jump straight to the remainder. H 1 over capital N factorial, I always forget those factorials. That times the nth derivative of h at tau times 1 minus 0 raised to the nth power. Like that. And that's just true because we already proved Taylor's theorem for h. But now we can translate it to f. So h of 1, we know, let me write just therefore. H of 1 is f of x. H of 0 is f of p. H prime at 0, we computed as the gradient of f at p dotted x minus p. And then 1 minus 0, every time we see that, that's just the number 1. Plus 1 over 2 factorial. And then this we explicitly showed was the Hessian of f at p acting on the pair of vectors x minus p, x minus p. And then I made a claim, and then I'm going to keep using the claim to write 1 over capital N. Tau is a value between 0 and 1. So we would plug that first into R, and it would take us to a point between 0 and 1, and that's what we will now declare as C. So this is going to be dn, the nth order derivative of f at p, sorry, no, exactly, at C. Again, with Lagrange's form, it looks so much like the Taylor polynomial that it like fits in nicely, but it also means that there's a little risk of not writing it correctly, times or acting on rather, x minus p paired up with itself capital N times. And then let me just write a note here and we'll wrap this up, where C is set to be R of tau. All right, I think we've done enough in this video, so I don't want to make a long speech. Now let me just say that we've reached the end of this proof, again with some details omitted. I have more examples with Taylor series where we will look at specific examples of series, or rather polynomials. So if you'd like to see these computations worked out for actual functions, we have follow-up videos about that.